When we think about how an AI learns, it's so easy to just picture some kind of magic happening inside a black box. But the truth, it's not magic at all. It's actually a really fascinating and kind of brutal mathematical process of trial and error. Today, we're going to pull back that curtain. We're going to see how an AI learns by enrolling in what we're calling the school of failure, where getting things wrong is literally the only way to eventually get them right. Okay, let's get into it. Here's our roadmap for today. First, we'll look at the emotional landscape, basically how you even begin to teach a machine about feelings. Then, we'll build a digital mind from the ground up. After that, we dive into the core of it all, the school of failure. And that's going to lead us to the most crucial part, the art of the step. Finally, we'll see what happens when these things are let loose in the real world. So where do you even start? I mean, think about it. You've got messy, subjective human feelings on one side and cold, hard numbers on the other. To bridge that gap, you can't just tell a machine to be happy. You have to give it a map, a mathematical grid where every single feeling has a coordinate. Without that map, the AI is completely lost. Okay, so it turns out there are basically two ways people have tried to draw this map. The first is like a Lego set. You have distinct, separate bricks for happy, sad, angry, and so on. It's simple, sure, but is that really how we feel? The other way, and this is where things get interesting for AI, is to see emotion as a rainbow. It's not a bunch of separate buckets, it's a continuous spectrum. Because, let's be real, life is lived in the shades between the primary colors, right? And the tool that lets us navigate that rainbow is called the VAD model. Honestly, the best way to think about it is as a GPS for your feelings. It plots any emotion on 3 different axes. First, you've got valence. That's just a scale from really pleasant to really unpleasant. Then there's arousal, which is the intensity. Think calm versus totally hyped up. And finally, dominance, which is all about how in control you feel. So suddenly, a complex feeling like fear isn't just a word anymore. It's a precise location, low pleasure, super high intensity, and a feeling of no control. And just like that, we've turned a feeling into data. Okay, so we've got our map. We have a way to turn feelings into coordinates. Now what? Well, now we need a traveler. We need the mind that's going to learn to read this map. And to build one, the pioneers in this field looked right at the blue part inside our own heads, the human brain. They decided to recreate biology, but with math. And you can see just how literal that inspiration was. In your brain, dendrites receive signals. In an AI, you've got inputs. In your brain, chemicals control how strong a connection is. In an AI, you have what are called weights, which are basically just little digital volume knobs that decide how much attention to pay to any given input. Then all those signals get added up, and we hit the big moment. In a real neuron, it decides whether to fire. In an AI, that's the activation function. And my favorite analogy for this is a grumpy bouncer at a club. It looks at the signal and decides, are you important enough to come in? If yes, the signal goes through. If not, you're out. So now we have our digital brain, but here's the thing. It's a complete blank slate. It's totally useless. An AI isn't born smart. It has to be trained. And that training is a process of optimization. It's a digital version of what scientists call neuroplasticity. The AI literally rewires itself over and over again by making mistakes and then correcting them. Its entire education is built on a foundation of failure. And the main teaching method in the school is something called backpropagation. The easiest way to get this is to imagine a game of telephone, but in reverse. So first, the AI takes a guess at something and, oops, it gets it wrong. Next, a special formula called a loss function calculates a score for how wrong it was. Then, and this is the key part, that error signal travels backward through the entire network. It goes from the final guess all the way back to the start. And at each step, it tells every single one of those little bouncers and volume knobs exactly how much they contributed to the mistake and how they need to change for the next try. It's basically a system for assigning blame. But here's the question. How does it know which direction to change in? That is where gradient descent comes in. And I want you to really lock in on this metaphor because it's everything. Imagine the AI is a hiker standing on the side of a huge mountain range, totally surrounded by a thick fog. That entire mountain range represents every possible mistake the AI could make. The hiker's only job is to get to the absolute lowest point, the bottom of the deepest valley. They can't see anything, but they can do one thing. They can feel the slope of the ground right under their feet. And that simple feeling of which way is downhill is the only guide they have. So, how does our hiker actually find their way? This is where it gets really cool. All of that complexity, this entire learning process, boils down to how that hiker takes a single step. We're about to look at the one line of math that acts as the hiker's entire instruction manual for getting down the mountain.
And this is it. Now, I know what you're thinking, but don't panic if you're not a math person. Seriously, this simple-looking formula is the entire rulebook. It tells the AI exactly how to update its brain every single time it gets something wrong. Let's just take a breath and break this down piece by piece. All right, first up is W, which stands for weight. Remember those little volume knobs? Well, W is just the current setting of all those knobs. In our hiker metaphor, W is simply the hiker's current position. It's where they are standing right now on that foggy mountain. The entire goal here is to find a new W that is a little bit further downhill. Next up, DW. The official name is the derivative, but forget that. Just think of it as the hiker's compass. It's the calculation that feels the ground and points in the direction of the absolute steepest way down from where the hiker is currently standing. It's the part that says, okay, downhill is that way. And finally, we get to maybe the most important part of this whole process. That little symbol that looks like a fish, that's alpha. It's called the learning rate, and this is absolutely crucial. If W tells the hiker the direction to go, alpha tells the hiker the size of the step to take. Is it a tiny shuffle or a giant leap? This one single number, decided by a human, controls how bold or how cautious our hiker is, and it will determine the success of the entire journey. And getting that step size right is everything. It's a total Goldilocks situation. If you set that learning rate alpha too high, our hiker takes these massive, reckless leaps. They feel a steep slope and they just go for it, jumping so far they completely overshoot the bottom of the valley and land way up on the other side. The AI just gets stuck bouncing back and forth, never finding the answer. But if you set alpha too low, the hiker takes these tiny, timid little shuffles. The process is so painfully slow, it might literally never get to the bottom. It just runs out of time. Okay, so let's say our hiker has found that just right step size. They're making good progress, moving steadily downhill. But there's another, much sneakier trap hiding in that fog. What happens if the ground suddenly feels flat and the hiker thinks, aha, I made it, I'm at the bottom, but they're not? This is the trap of the false valley. In machine learning, it's called a local minimum. It's a little dip on the side of the mountain that feels like the bottom. Because from where the hiker is standing, the ground is flat in every direction, so their compass says there's no more downhill to go. So they stop. They think they're done. But the real goal, the true deepest point, the global minimum, is way over in another valley, much further down. An AI that gets stuck here is, from its point of view, fully optimized. It thinks it has the best possible answer, but it is still completely wrong. It has become confidently incorrect. And this, right here, is where all this math crashes into our everyday lives. Because getting stuck in one of those false valleys isn't just a quirky computer problem. When we start using these AI systems to make huge decisions about people's lives, a local minimum can have some really serious real-world consequences. Let's look at a company like HireVue, which uses AI to scan video job interviews. If its hiker gets stuck in a local minimum, defined by, say, one specific company's culture, it might start thinking that only people who talk and act that way are top performers. It could penalize someone just for having a different communication style. Or think about Effectiva. Their AI learned to read faces from a huge database labeled by people in Cairo. This brings up something called social reality, the idea that a scowl doesn't always mean anger. In one culture it might, but in another it might just mean you're thinking really hard. An AI stuck in the false valley of one culture is going to get that wrong, a lot.
So that was a lot. Let's do a quick lightning round. We started with the VAD model, our 3D emotion map. We used weights to control attention. We learned how backpropagation sends feedback to correct mistakes, and how our gradient descent hiker uses the learning rate, alpha, to get down the mountain, trying not to overshoot or get stuck in a local minimum. We saw how social reality makes this all super tricky, which is why experts want to use multimodality, fusing data from the face, voice, and context, especially when an AI is learning in the wild.
And all of this leads to a pretty fundamental choice. Are these systems, with their foggy hikes and hidden false valleys, going to become our judges, using logic we can't see to decide who gets a job or who's a threat, or could be something else? Some have suggested that in tragedies like the Tanjong Pagar crash, an AI using multiple data sources could have acted as a protector, a guardian that noticed the risk before it was too late. The same math can lead to either outcome. Because in the end, that's what these algorithms are. They're mirrors. They don't have their own ideas. They just find patterns in the world we show them, a world with all of our biases, our nuances, and our flaws. So the biggest question isn't really about the technology. It's about us. As we build these incredible machines that learn from our world, which version of that world are we actually asking them to reflect?